You guys remember this guy? Coulomb's law?
A little bit.
More or less than more. So Coulomb's law says that the energy of assembling two charges, Q1 and Q2, right, is proportional to the multiplication of those charges divided by the radius that separates them times a constant. You guys remember this? Kind of, sort of? Kind of, sort of.
Oh, so the smaller radius makes it more attractive, right?
Right, so closer together, right, is going to make the attraction greater. Only if these guys have opposite charges, right? If they have like charges, then they'll repel. So when we talk about a strength, the strength of oh my god, ionic bonds, the two big things that are going to mitigate the energy of those bonds or the strength of those bonds are, number one, R, which is the distance between positively charged nuclei.
Mm-hmm.
Right? What's the other thing? So if Q is the charge, right? Then the higher the charge of the ions,
Right.
the higher energy. Does that make sense?
Because they're sharing more electrons or something? Because they want to, like...
It's more about, so Coulomb's law is giving you information about the electrostatic potential, which is a fancy way of saying that opposite charges are attracted to each other and like charges repel, right? But we want to know not just, so we know that that's the case, right? That like charges are repelled and that opposite charges are attracted, but we want to be able to quantify that, right? So Coulomb's law gives us information about the strength of an ionic bond. Does that make sense?
Mm-hmm.
And the two big factors when you're talking about the strength of ionic bonding are the charge magnitude and the radius between the atoms, or ions rather, excuse me. Coolsies? So this is something that we'll come back to, I think you talk more about this in Chem 201, maybe a little bit. But the main reason why I'm bringing this up is because this idea of ionic bonding is really all about electrostatic interactions. Right, which is opposite charges attraction. Specifically looking at the strength of that attraction, right? Does that make sense, guys? Any questions about that? We're cool.
What does the bottom say, like, below electrostatic?
Better?
Okay.
Sorry. So the reason why I wanted to make sure we touch on this is because electrostatic interactions occur between ions that have formal charges, but those electrostatic interactions also occur between molecules that are polar, right? They're not nearly as strong because they don't have formal charges, but it's the same type of interaction that we're dealing with. So, when we're talking about polar molecules, right, what are the two main factors that have to be true in order to have a polar molecule? What do you have to have?
Unequal distribution of electrons.
That's true, but I'm thinking more in terms of the Lewis structures.
So it would be not symmetrical?
Yes. So we would have asymmetry, right? And there's two main types of asymmetry that we can have, right? Do you guys remember those?
Mirror, or I don't know, actually.
You're thinking chirality, I think, which is fun, but no.
Yeah.
So asymmetry could mean that we have lone pairs, right? Lone pairs, any geometry that includes lone pairs will be asymmetric by definition, right? The other way that we can have asymmetry in a molecule is by having different attached atoms. Okay. So what do I mean by different attached atoms? So if I have a molecule like these, right? What's that guy called?
Carbon tetrachloride.
Yeah, carbon tetrachloride, right? Polar or nonpolar?
Nonpolar.
Why?
It's symmetrical.
Is symmetric. Does everybody see that? Yes? No?
Yeah.
Cool. So, one of the ways that I can create asymmetry in this molecule would be having different attached atoms.
Okay, so basically like more than two different kinds of atoms.
Exactly, yeah. So we know that carbon and hydrogen, right, are not going to have polar bonds. You with me there? We know that carbon and chloride will have polar bonds, right? But that all of these dipoles are pointing in opposite directions, and so they cancel out, right? But as soon as you replace one of those atoms with a different atom that's nonpolar, now you have a net dipole. What direction does it point?
Downward?
Down, exactly, right? So you would have a partial positive around the carbon and a partial negative pointing down. Does that make sense, guys? So is everybody comfortable with the two main types of asymmetry in a molecule? This is a really good opportunity for you guys to talk to me if you don't understand this, because if you're going on to organic chemistry, this is organic chemistry. Like on steroids, this times 1,000.
So only the one on the right is asymmetrical?
That's correct. So we have asymmetry with different attached atoms, right? And this one is symmetric. Whoops. So, symmetric, nonpolar. Even though we have polar bonds, the molecule is nonpolar. Right? Over here, because we have asymmetry and polar bonds, we have a polar molecule. Does that make sense, guys? You picking up what I'm laying down?
Is that a positive going down on the second one?
The positive is by carbon, right?
Mm-hmm.
Because carbon is less electronegative than chlorine. Right?
Okay.
So the positive end is always the butt of the arrow. The tip of the arrow is always the negative end.
Oh.
So the way that we would indicate these with our partial charges, we would have a partial positive charge by the carbon and a partial negative charge down at the bottom. Does that make sense, guys?
Yeah, that helps a lot.
Yeah, cool. So, so we said asymmetry, right? And polar bonds, right? So if you don't have any polar bonds to start, then there's no way you can have a polar molecule, right? Does everybody remember the two ways that you can have a nonpolar bond? This is going to be important.
So like a bond between carbon and hydrogen or something?
Yep, that's one of them. So nonpolar bonds. So the easier thing to remember is not who makes polar bonds, but who makes nonpolar bonds, right? So if we have carbon bonded to hydrogen, that's going to be nonpolar. What's the other case?
When they're really close together in electronegativity, so they cancel out.
Specifically, what did we say is the rule?
Is it like when it's less than 0.04?
That's the technical rule, but we said that there's because that's too hard to remember. You can't. I don't expect you guys to memorize electronegativities, right? So
if it's bonded to itself.
That's exactly correct, right? So if you have a carbon and a hydrogen bonded, nonpolar, if you have anything bonded to itself, right? So examples of that would be diatomics, right? You guys picking up what I'm laying down?
Mm-hmm.
So anything that's bonded to itself will be a nonpolar bond. Does that make sense, guys?
Could you draw an example?
Yeah, of course. So, right, this guy is definitely nonpolar, right? Nothing but carbon and hydrogen. If we had this guy, right? That's, what's this guy's name?
Oxygen.
Oxygen, right? So oxygen and all the other diatomics just have bonds with themselves, right? Anytime you have something bonded to itself, the electronegativity difference is 0, right? This means that they're equally sharing. Even though oxygen is very electronegative, when it's bonded to itself, it doesn't have any difference in electronegativity, right? Now, strictly speaking, these are not the only two examples of how you can have a nonpolar molecule, right? We know that polarity and polar character or ionic character are a spectrum, right? They range from being really, really highly polar all the way up to ionic. down to completely nonpolar, right? But without having an electronegativity table sitting right in front of you, I don't expect you to know the electronegativity difference between every single atom, right? Does that make sense? So this is a pretty good fallback position, right? Because these are the two main examples that are always going to be nonpolar. Not these particular molecules, but the rules that we put on the previous page. Does that make sense, Teddy? And Daisy and everybody?
Yes.
Cool.
Yeah.
I remember you saying though, like if the atoms are like pretty close in electronegativity, then they just like cancel out. Like if they're next to each other on the chart or on the periodic table or something.
No. So electronegativity, we said increases as you go across the periodic table.
Mm-hmm.
Right? And then decreases as you go down.
Right.
Right? So, yeah, we'll look more at that when we get into the PowerPoint. But
Okay.
no,
So, like,
the electronegativity values are given on the periodic table. If we go to the dynamic periodic table, there's also one in your textbook, right? But your technical rule for when you have a polar bond is any difference in electronegativity of 0.4 or greater. I think when you get up to like 1.2 or something difference, that's when you cross the border between polar covalent and ionic, right?
Right. So like the like a bond between nitrogen and oxygen. Do you know if that's polar or non-polar?
Yes, absolutely, it would be polar.
It is polar.
Mm-hmm.
Okay.
Yeah, and again, I'm kind of oversimplifying things, right? There will be plenty of time for nuance in understanding bond polarity in its specifics. But for this class, what I want you to understand is just the basics, right? So again, am I oversimplifying? Yes. But my oversimplification is so that we make sure that we get a solid footing in understanding polar versus nonpolar before we move on to the nuances. Does that make sense?
Mm-hmm.
Questions about that? So, extremely important in this chapter to be able to look at a molecule and understand whether or not it's polar or nonpolar. Okay? So if that was something that you were struggling with in chapter 8, right, you want to make sure you go back to that and review it. Okay? Okay, so now we're going to get into some of the new stuff, right? So we talked about intramolecular forces, which are the forces that hold atoms together in a molecule. Intramolecular are the glue holding atoms together. Now we're going to talk about intermolecular forces. Which I will abbreviate as IMF because I am far too lazy to write this over and over again. So where we said intra means within the molecule, inter means between
The molecules, right?
Exactly, between the molecules, right? So these are the attractive forces that allow molecules to condense to form solids and liquids. Right? So, in terms of the relative strength, intermolecular forces are like glue. These are bonds that require a relatively high energy cost to break, right? When we break them, they release a tremendous amount of energy, right? So if you remember when we were talking about exothermic versus endothermic, right? When we were talking about burning things, that's a really good example of breaking a lot of bonds, right? When we break a lot of bonds, we release a lot of energy, right? Intermolecular forces at their strongest are maybe 10% of covalent bond strength. Right? So that's at their very, very highest. Okay? So these are considerably weaker than true bonds. So I liken intermolecular forces to Velcro.
Does that say maybe 10%?
Maybe 10%. Yeah, sorry, that's ugly. I don't think I made it better. Sorry. Right, so intermolecular forces are the Velcro between molecules. People have experience with Velcro, right? You guys know what I'm talking about.
Yeah, shoes as a kid.
Yeah. I know we don't deal much with Velcro as adults, but you guys get the analogy, right?
Yeah.
So you can have Velcro that's relatively strong and kind of hard to pull apart, right? It's still nothing as strong as glue, right? Glue, you probably end up ripping something when you try and get them apart. But you could also have Velcro that's really worn out and barely sticks things together, right? So that's kind of more the range of attraction that we're talking about with intermolecular forces. Okay. So there are 4 basic flavors of IMF. And we're going to start with the strongest.
Hydrogen.
We'll get there. Strongest? There it is. Oof, it's not cute. Okay, so the first one is called Ion-Dipole Interactions. Okay. So, just to get us back on track, the dipole, what does that word mean? What does it mean to have a molecular dipole?
Polar?
Polar, right? Which means you have a separation of charges, right? So you have partially positive on one part of the molecule and partially negative on another part. Does that make sense, guys?
Mm-hmm.
Cool. And ion is something that has a formal charge, right? Does that make sense, guys? So what might be an example of an ion-dipole interaction that you guys are familiar with? So what is an instance that you have a polar molecule that is interacting with ions? Think chapter 4.
Is that like surface tension
Mm-mm.
between water? No.
It has to do with water.
Oh, because surface tension is cohesion, like adhesion between water.
Yeah, but we're not talking about water being attracted to itself right now.
No, but I'm talking about adhesion, which is water being attracted to something else.
Right. So all of our IMFs have adhesive qualities, yes. But specifically, I'm thinking of ionic salts dissolved in water, right?
Okay.
So, when you have an ionic salt and you put it in water, right? You guys remember we talked about this a million years ago in chapter 4?
Yeah.
Right? We said that the way that an ionic salt is dissolved in water is because the water molecule has that partially negative oxygen and a partially positive hydrogen zone, right? And if we have something like, say, a sodium ion, right, that's going to be attracted to that partial negative on oxygen, right?
Oh yeah, the blanket thing you talked about.
Yeah, the blankie. Solvation blankie. Does that make sense, guys? So this is one that we've kind of already talked about, but we're just formalizing our understanding now, right? So ion-dipole interactions are the strongest because they involve a formal charge, right? So when we're looking at the electrostatic potential, right, using Coulomb's law, you guys remember the charge relationship there, right? Charge times a charge. So if you have a full charge, that's going to be a stronger interaction than just having partial charges interacting with each other. Does that make sense? Because the magnitude of the charge is greater.
Wait, so you said the formal charge is stronger than the partial charge.
Right. So let's say we're talking about a sodium ion, right? Sodium ion has a formal charge of +1, right? I don't know exactly what this partial charge is, but let's say at its strongest, it's -0.5 maybe. That's probably a gross overestimate. But do you guys see how these two numbers are going to make a much smaller energy than an ion-ion interaction would? And how if we just had two partial charges, that would be significantly smaller of an interaction than when we have a formal charge. Does that make sense?
Yep.
Questions about that? We're okay. Cool. So ion-dipole interactions we're going to come back to in chapter 12 when we talk about solutions, because that's going to be a big part of talking about solutions, okay? So ion-dipole are the strongest interactions. The next strongest are, dipole-dipole interactions. So dipole-dipole interactions are exactly what they sound like. We have molecules that are polar, organizing, so that the partial positive and, oops, partial positive of one molecule is aligned 1L with the partial negative on another molecule. Right? So you have two charged particles, right? Let's say we're talking about this guy that we were talking about before. Right? We said that there would be partial negative on this end of the molecule and a partial positive on this end, right? So what will happen is you'll get these molecules organizing so that you have the partial positive ends hooking up with the partial negative ends on another molecule, right? And you can imagine that going on and on forever, infinity times. My wavy lines are their attraction. Does that make sense, guys? Questions? We cool? Cool. So, dipole-dipole interactions require that you have polar molecules, right? Now, there's a subtype of dipole-dipole that is the strongest type. Of dipole-dipole.
But it's still not stronger than ion-dipole.
Correct, right?
Oh.
So ion-dipole is still the strongest, but this is the strongest subtype of dipole-dipole, and that is hydrogen bonding. Right? And the word bonding here is really a misnomer, right? Because hydrogen bonds are not nearly as strong as a true bond. These are about 2 to 5% the strength of a covalent bond. Right? So much less strong than a covalent bond. Questions about these guys? Cool. So hydrogen bonds can only occur when you have hydrogen bonded to oxygen, hydrogen bonded to nitrogen, or hydrogen bonded to fluorine. Okay? These are the only 3 bonds that can hydrogen bond.
Okay, so that's the only options that this type of dipole-dipole hydrogen bond can happen with.
Exactly, right?
Okay.
So when you talk about dipole-dipoles, generally, a hydrogen bond is a type of dipole-dipole. It's the strongest type, but not all dipole-dipoles are hydrogen bonds, right? The only dipole-dipole that are hydrogen bonds are ones that involve hydrogen bonded to oxygen, hydrogen bonded to nitrogen, or hydrogen bonded to fluorine. Okay. Questions so far? So let's talk about why those are the strongest type of dipole-dipole. So hydrogen bonds, which I'm never going to write again, H bonds from now on, right? Hydrogen bonds always involve hydrogen-oxygen, hydrogen-nitrogen, or hydrogen-fluorine bonds, right? So it's not enough to just have hydrogen and oxygen in a molecule, okay? They have to be bonded together, okay? So let me give you an example. If we have this molecule, right? Hopefully you guys maybe can't see just by looking at this, but hopefully you have a little bit of intuition about the connectivity of the atoms, right? So this molecule is going to have carbon in the center, hydrogen, hydrogen, and oxygen up top here, right? So even though the molecule has hydrogen and oxygen, right, it doesn't have hydrogen bonded to oxygen, right? So no H bonding. Oops, sorry. Does that make sense, guys?
Yep.
Cool. So, why are hydrogen bonds so strong? Hydrogen has one lonely electron, right? And oxygen, nitrogen, and fluorine, right? What do we know about their electronegativity?
Tie.
Not a tie. Who's the strongest?
Oh, fluorine.
Fluorine, right? So we know that these guys increase in electronegativity as we go down, right? But of all of the nonmetals, these guys are the most electronegative, right? You guys picking up what I'm laying down here?
Yeah.
So, if these guys are all extremely electronegative, right, and hydrogen only has one electron, then when we have these guys bonded together, right, we know that that one little electron that hydrogen came with is basically being completely owned by fluorine over here, right? Does that make sense, guys? So this dipole is incredibly strong, right? When you have hydrogen, which only has one electron, and it's being pulled away from it, what are you left with that hydrogen?
Just a proton.
Just a proton, right? Does that make sense? So this is almost a positive charge, right? Because once it gets that electron taken off of it, right? And it may not be 100% pulled off, but it's pulled off enough that this charge, this positive charge, is pretty bare, right? So it's very close to being a formal charge. Does that make sense, guys?
I have a question.
Yes.
So the positive arrow thing,
Yes.
it's positive on the hydrogen because the electron is getting pulled over to the fluorine, so it's creating a more positive
Exactly.
area.
Exactly. So what we're saying here is we're saying that fluorine is yanking the electrons this way, right?
Mhm.
And so when you take the electron density off of hydrogen, right, what's left over?
Just the proton.
The proton, right? Or the partial positive charge, right? So when we're talking about electrons, right, we're always talking about areas of extra electron density, aka partial negative charges, and electron deficits. So we have areas of electron deficit, right? These are the areas that have partial positives. Right? So really everything that you guys are going to talk about if you go on to organic chemistry is all about where you have extra electrons and where you have not enough electrons, because that separation of charge is what defines all of the behavior in organic molecules, okay? So I can't overemphasize how important this stuff is. Unless you're not going on to organic, and then forget about it, right? Cool. So is everybody pretty clear about why hydrogen bonds are the strongest type of dipole? There's no other atom that you can get this kind of naked positive charge with except for hydrogen, right? Does that make sense, guys? And specifically, it's when hydrogen is bonded to these really electronegative characters, right, that you get that very strong dipole. Okay? Everybody comfortable with that? And everybody comfortable with the fact that it's not enough just to have hydrogen and nitrogen or hydrogen and oxygen in a molecule, right? They have to be bonded together, right? Like this. Questions? We cool? Cool. All right. So the last type of intermolecular force is the weakest, and that's called dispersion or London forces. Okay. So dispersion forces can occur in all atoms and molecules interacting. Okay, so everybody can have dispersion forces, but if there's stronger intermolecular forces, then those will be the dominant intermolecular forces, right? So the dispersion forces being the weakest one, let's say we were talking about our water molecule, right? What kind of intermolecular forces does a water molecule have?
You said intra?
Inter.
Hydrogen.
Hydrogen bonds, right? If you said dipole-dipole, that would also be acceptable, right? What else?
London dispersion.
So even though water has those stronger attractive forces, it also has dispersion forces, right? But that wouldn't be the dominant intermolecular force in water, right? The dominant intermolecular force in water would be H bonds. Does that make sense? But it doesn't mean that it doesn't have dispersion forces. Coolsies? You with me? Cool. So what the heck are dispersion forces? So you guys can imagine my drawings are going to get really bad at this point. And again, I have pretty pictures on the slides. We'll look at those soon, right? You guys can imagine that this is my picture of an atom with a positively charged nucleus, and the electrons are floating around on the outside. Now, I drew the electrons far apart. Why?
Because they repel each other.
Yeah, electrons repel each other, right? So whenever they can, they're going to try and organize as far apart as possible, right? But are electrons just sitting in place?
No.
No, never, right? They're flying around all over the place, right? So even though this is the most energetically favorable, it doesn't mean that it's the only way that the electrons can be organized, right? Far from it. So you guys can imagine that it's possible, even if it's not energetically favorable, that you could have this orientation of electrons, right? You guys picking up what I'm laying down? So this would be temporary, right? Because the electrons repel each other. But it can occur, right? When you have this kind of temporary arrangement, you get what's called a temporary dipole. Right? So even though this arrangement of electrons is not favorable, which means that it's not super probable, right? It can happen. Does that make sense? You guys tracking live with me?
Yeah.
Cool. So you can imagine if we have two atoms, right? That if we bring those two atoms together, right? What's going to happen to the electrons when we bring these guys closer together?
Would the electrons from one of the atoms kind of move to the outside?
Yeah, exactly, right? So we have these electrons over here are going to repel this electron over here, right? So it's going to make this electron migrate farther to this side. So what we end up with is we have these electrons over here, and again, this is, you know, kind of bidirectional, right? So it's not like it's only happening in one direction, right? But these electrons over here being repelled to one side, setting up this partial negative on this side. As these guys are being repelled, now we're setting up a partial positive on the other side, right? That partial positive is attracting the electrons on the other side, setting up a partial negative, and then another partial positive, etc., right? This is called an induced dipole, right? So as atoms or molecules come in contact with each other, right, you can have this kind of induced dipole. Does that make sense, guys?
Yeah.
Does it make sense to you guys why this is such a weak interaction?
Yeah.
It's definitely not energetically favorable to have these kinds of arrangements of electrons, right? They don't want to be next to each other if they don't have to be. We cool? Cool. So when we talk about dispersion forces are the dominant intermolecular force in gases, right? Which is to say there are not a lot of attractive forces between gas particles, right? So, like we said in chapter 5 when we were talking about gases, we said that the attractive forces between gas particles are negligible, right? And that's true under certain conditions, right? Where we have very dispersed gases at regular pressures. But as soon as we start getting these molecules closer and closer together, right? These intermolecular forces, weak though they are, become stronger and stronger until you start getting condensed phases, right? So if you put nitrogen gas, for example, under a lot of pressure, what happens to it?
It'll liquefy.
Yeah, you can get it to liquefy. Have you guys ever played with liquid nitrogen before? I hope for you guys that you get to play with it at some point. It's very fun. So liquid nitrogen can only occur under tremendously high pressures, right? And the reason for that is because at high pressures, you get these kinds of induced dipoles, right? So even though this is a very nonpolar molecule, right? The molecules are not very attracted to each other under normal gas conditions, but under high pressures or high densities, this attraction starts becoming strong enough to make a condensed phase. Does that make sense, guys? Picking up what I'm laying down? Questions? We cool? All right, so let's look at some examples. Okay, so right? So let's talk about these guys, right? What are the dominant IMFs in each one of these examples? So what about the first one?
SI.
Hmm?
SI.
Yes, so this is silicon tetrahydride, right? What are the dominant intermolecular forces present? Or what is the dominant intermolecular force present?
Hydrogen bond?
Can it hydrogen bond?
No.
No, right? No oxygen.
Dipole?
Is there a dipole between hydrogen and silicon?
No.
Pretty nonpolar, right? Silicon sits right below carbon, right? So it's going to have very similar behavior to carbon in terms of its electronegativity, right? So this molecule is going to be nonpolar, right? You guys picking up what I'm laying down? So, dominant intermolecular force would be?
Induced dipole.
What do we call it?
Oh, London dispersion.
London or dispersion forces, right? Does that make sense, guys?
No.
So, if we have silicon in the center and hydrogens all around it, right? This is going to be pretty nonpolar.
So I'm following all that.
Yeah.
I get how it's nonpolar, but then how are you saying it's... Oh, because dispersion's temporary, so it could...
So what we're saying is if we don't have a polar molecule, right? Then we can't have stronger intermolecular forces between these guys than dispersion forces. Does that make sense?
Because all molecules have dispersion forces, but not all molecules have a stronger
Yes,
force than that.
exactly.
Which that one doesn't because it's nonpolar.
Correct.
Okay.
Let me see.
Because I said hydrogen bond at first, but it would have to be polar for that to be true, because
What are the atoms that are able to do hydrogen bonds?
Chlorine,
polar atoms, water.
Nitrogen.
There's specific bonds
Oh,
involved.
sorry. You said like fluorine, nitrogen, and oxygen?
That's correct, right? So if we look at the actual electronegativity for silicon, and I wouldn't give you this one on an exam because this is one of the exceptions, right? Silicon has an electronegativity of 1.9, right? And hydrogen has an electronegativity of 2.2, right? So the difference in electronegativity between these two guys is 0.30, right? So this is a relatively non-polar bond. It's actually less polar than carbon and hydrogen. Okay? Again, that's an exception. I wouldn't give you that on a test, but I'm just trying to get your gears turning, okay?
Are you gonna ask us about the electronegativity difference?
I don't. If there might be some problems in the homework that get into that, but what I would like you guys to know about the electronegativity difference is the periodic trend, not the actual values. Does that make sense?
Okay.
Yeah. So, and again, if we're looking at carbon and silicon on our periodic table, right? What happens to electronegativity as we go down the periodic table? Decreases, right? So if we know that carbon and hydrogen are going to make a nonpolar bond, right? And silicon is even less polar than carbon, then it stands to reason that this would make a nonpolar bond with hydrogen also. Does that make sense, guys? Again, wouldn't test you on it, but just trying to get you guys through some of the logic here. Cool? Questions about that one?
So are all non-polar bonds going to be dispersion forces?
Correct, right? Technically, all bonds will have dispersion forces, right? But they're only going to be the dominant. They're only going to be the dominant intermolecular force if there's no other stronger intermolecular forces there. Okay, does that make sense? What was your question, Harrison? I'm sorry.
Or if it's a gas, right?
So that's two ways of thinking about it, right? So generally speaking, gases will usually have only dispersion forces, right? Now, when we're looking at dispersion forces in gases, there are other factors that come into it, and we'll talk more about that. Okay? So, dominant intermolecular force in chlorine.
Is that the Ion-Dipole Interactions?
What did you say, Harrison?
It's going to be dispersion because it's two of the same things, so the electronegativity difference is 0.
Exactly. Right? Does that make sense, guys?
Yeah.
Let's see.
So how about this guy?
Hydrogen bond.
Hydrogen bonds. Everybody okay with that? Questions? What about this guy? Polar, non-polar?
Polar.
I think it's symmetric, right?
Yeah, so now this is one of the areas where guessing is really not going to serve you, okay? So this molecule could have a lone pair on it, right? If it has a lone pair, then it's asymmetric. But if it doesn't, then it's probably symmetric, okay? So we really need to draw this guy to be able to see that it's nonpolar. I just happen to know that that's what the structure looks like, so if you didn't do that in your mind immediately, that's totally fine. But that's the structure of sulfur trioxide, right? So when you look at the structure, I think it's a little bit easier to see that it's nonpolar, right? Does that make sense?
Yeah.
So then what are the dominant intermolecular forces here?
Dispersion.
Dispersion. Right? So when in doubt, draw the molecule, okay? Because it is really easy for this chemical formula to hide connectivity and the fact that there may or may not be a lone pair on that central atom, right? Questions about that, guys?
So it's nonpolar. Why?
Because it is symmetric,
Okay.
right? So anytime you have a symmetric molecule, meaning there's no lone pairs and all of the attached atoms are the same, right?
Oh yeah.
It is nonpolar. If it's nonpolar, then it only has dispersion forces, right? Does anybody happen to know what state this is in under normal ambient conditions?
Gas.
It's a gas. Yeah, absolutely. Sulfur trioxide is a gas. Cool. So, how about this guy?
Hydrogen.
Hydrogen bonding, says Harrison. What do you guys think?
Yeah.
Yeah.
Yeah, I agree, but just to be safe, it's a good idea to draw it. Right? I don't know if you guys have just happened to have done this structure enough times to recognize that nitrogen tends to have lone pairs, or a lone pair, right? So this guy has hydrogen bonds because it's asymmetric, right? But if this was a symmetric molecule, then it would not have that same polarity. Does that make sense? You cool with me? So, hydrogen bonds.
So, in this one,
Mm-hmm.
if you were to draw the little plus arrow thing,
Mm-hmm.
would all three of the hydrogen bonds have a plus arrow to the lone pair?
Yeah, so basically what you end up having is the net dipole is pointing up at the nitrogen, right? So there's an area of partial positive in this base of hydrogens. Does that kind of make sense? So each one of those hydrogens carries a little bit of that positive charge, right? Where nitrogen is carrying, all of the negative charge. Does that make sense?
So you wouldn't really think of it as like three arrows.
No, you don't think about it as three arrows, but you can think about the electrons. So this is where it gets kind of difficult because without looking at a three-dimensional structure, it's kind of hard to see this, right? But this has a tetrahedral electron geometry, right? So the nitrogen is sitting up top, and there's kind of a triangular base of hydrogens underneath it, right? So the nitrogen has the partial positive, and the base of the hydrogens share that partial, I'm sorry, I said that backwards. The nitrogen has a partial negative, right? And the base of the hydrogens are sharing that partial positive. Does that kind of make sense?
Mm-hmm.
Cool. Questions about this one, guys? What do we think? This all right?
Yeah.
Yep.
Cool. So again, on Thursday, we'll look at some prettier pictures, and hopefully that will help kind of solidify this picture for you guys. But I like to go through it the first time in just a very basic written form because I think it helps stick everything together. So.